Solve problems on numerical integration. I start by reviewing the subject matter. Recall that definite integrals were defined in terms of Riemann sums. A Riemann sum for a function f is formed so that the interval in question from a to b is divided into subintervals. And over each subinterval one places a rectangle that best approximates the domain between the graph of the function f and the x-axis. These rectangles are formed so that in each subinterval one chooses a tag point tk, and the height of the rectangle is the value of the function f at this tag point. If the value is negative, then the area of the corresponding rectangle is computed as negative in the Riemann sum. So in the Riemann sum for a function f over an interval from a to b is of this form: summation k from 1 to n, f evaluated at the tag point tk times delta of xk, where delta of xk is the length of the kth subinterval. The Riemann sum is the combined area of the blue rectangles minus the combined area of the red rectangles. Then one takes a limit. One lets the width of these rectangles approach 0, and at the limit one gets the value of the definite integral from a to b, f of x dx. This is how the definite integral is defined in terms of these Riemann sums. This definition allows us to approximate values of definite integrals easily. Mainly, we may simply compute some specific Riemann sums, and they are approximations of this definite integral. So we approximate the definite integral so that we decompose the interval of integration from a to b into some number n subintervals. The length of each subinterval is chosen to be always the same. So it is delta of x, which is b minus a divided by n, because we decomposed the interval from a to b into n subintervals. The kth subinterval has its endpoints at a plus k minus 1 times delta of x and at a plus k times delta of x. We choose the tag points tk from these subintervals, and we form the Riemann sum, summation k from 1 to n, f evaluated at the tag point tk times delta of x. That is the area of the corresponding rectangle, assuming that f is positive at the point tk. If f is negative at the point tk, then this is negative of the area. And the tag points can be chosen freely. They must be in the corresponding subinterval. So each tk is between a plus k minus 1 times delta of x and a plus k times delta of x. Otherwise, there are no restrictions. And this freedom to select tag points freely allows us now various ways to approximate definite integrals. The first approximation for the value of the definite integral from a to b, f of x dx, is the left approximation. That is where we choose the tag points tk to be the left endpoints of the corresponding subinterval. So tk is a plus k minus 1 times delta of x, and the left approximation is summation k from 1 to n, f evaluated at a plus k minus 1 times delta of x times delta of x. The right approximation uses the right endpoints as tag points, so the right approximation right n is summation k from 1 to n, f evaluated at a plus k times delta of x times delta of x. Then we have the midpoint approximation, where we choose the tag points to be the midpoints of respective subintervals. So now tk in the mid-n approximation is a plus k minus 1 times delta of x plus 1/2 delta of x. That is k minus 1/2 times delta of x. The trapezoidal approximation is the average of the right and left approximations. The trapezoidal approximation has also a geometric interpretation. The Simpson approximation is in many cases the best. It is 2 times midpoint approximation plus trapezoidal approximation divided by 3. These numerical approximations have the following property, which is immediate by the definitions. If the function f is increasing, then the left-hand approximation is at most the value of the definite integral from a to b, f of x dx, and this is at most the right-hand approximation. This follows since the left-hand rectangles lie below the graph of f if f is increasing, and the right-hand rectangles extend above the graph of f is increasing, as shown in these pictures. So this is first useful observation. This allows us also to understand how accurate our numeric approximations are. If we know that f is concave up or concave down, then we can still improve these approximations. If f is concave up, then left-hand approximation is at most, mid-end approximation is at most the value of the definite integral from a to b, f of x dx, and this is at most trapezoidal approximation, which is less than or equal to the right-hand approximation. So if f is concave up or if f is concave down, then the mid and trap approximations are better than the left and right approximations. If f is concave up, then mid approximation is less than or equal to the value of the integral, and the trapezoidal approximation is greater than or equal to the value of the integral. If f is concave down, then these inequalities are reversed.